Earlier this month, a rocket lifted off from China's Wenchang space launch site. At first glance, it looked like another routine test flight, but this mission combined multiple firsts in a single launch: a new heavy-lift rocket, a next-generation crew capsule, and an experimental recovery system at sea. For a country aiming to land astronauts on the moon before 2030, this was not just a demonstration. It was a coordinated rehearsal of several systems that would have to work together in deep space, under conditions where there are no second chances. The details of this flight matter because they reveal how China plans to close the remaining gap between Earth orbit and the lunar surface. So let's take a closer look. If you value clear, step-by-step breakdowns of complex space missions without hype or speculation, consider supporting the channel. It helps keep this kind of analysis coming. On February 11th, at the Wenchang space launch site on China's southern coast, a prototype version of the Long March 10 rocket lifted off, carrying a new generation crew spacecraft. The launch took place at 11 a.m., China Standard Time, and marked the first ignition flight of this specific rocket configuration. The mission was designed to test two major systems at once. First, it evaluated the ascent performance and partial recovery profile of the Long March 10 test booster. Second, it conducted a high-stress abort demonstration of the new crew capsule during the most demanding phase of launch, known as maximum dynamic pressure, or Max-Q. This is the point when aerodynamic forces on a rocket are at their highest. During the flight, the capsule's escape motors activated while the booster was still under power, separating the crew module and allowing it to descend safely under parachutes. Meanwhile, the booster continued along a controlled trajectory and later splashed down at sea. Recovery operations were also part of the demonstration, including testing coordination with a sea-based retrieval vessel. To understand why this single test matters, we need to break down what was actually being validated. The mission combined three major technical elements: the launch vehicle, the abort system, and the recovery concept. Let's start with the rocket itself. The Long March 10 is being developed as China's heavy-lift vehicle for future crewed lunar missions. Heavy-lift simply means a rocket capable of carrying large payloads beyond low Earth orbit. For comparison, sending astronauts to the moon requires significantly more energy than reaching an orbit a few hundred kilometers above Earth. The moon is roughly 380,000 kilometers away, and reaching it requires both higher speed and more propellant. In this test configuration, the booster was powered by 5 YF-100K engines. These engines burn kerosene and liquid oxygen, a propellant combination known for reliability and high thrust. During ascent, the rocket must pass through what engineers call maximum dynamic pressure, or Max-Q. This is the point when atmospheric density and vehicle speed combine to create peak aerodynamic stress. Structurally, this is one of the most demanding moments of flight. The test was designed to trigger the capsule's abort system precisely during this phase. An abort system is essentially a set of dedicated motors mounted on top of a crew capsule. If a failure occurs during ascent, such as engine malfunction or structural instability, the escape motors ignite and pull the capsule away from the rocket in a fraction of a second. In this case, the capsule separated while the main engines were still firing. That detail is important because it simulates a real emergency scenario rather than a controlled shutdown. Once clear of the booster, the escape system reoriented the capsule into a stable descent configuration. The escape tower was then jettisoned, reducing weight and allowing parachute deployment. The descent sequence began with drogue parachutes, which are small stabilizing chutes designed to slow and align the vehicle. These were followed by larger main parachutes that reduced velocity to a safe splashdown speed. While the capsule descended independently, the booster continued along a planned trajectory. Instead of shutting down immediately, The booster throttled down from 5 engines to 3 and climbed to near space altitude. On the way back down, it deployed 4 grid fins. Grid fins are lattice-like control surfaces that allow a descending rocket stage to steer aerodynamically through the atmosphere. They function like adjustable air brakes, guiding the booster toward a targeted splashdown zone. The engines reignited briefly during descent. One burn helped reduce velocity as the stage re-entered denser layers of the atmosphere. Another short burn simulated a landing maneuver, even though the booster ultimately splashed down in the sea rather than landing on solid ground. This leads to the third technical component, recovery. Most reusable rocket systems rely on landing legs that deploy shortly before touchdown. In this case, China is exploring a different approach. Engineers are testing a net-style or cable-based capture system. Instead of landing on legs, the booster would descend toward a platform where tensioned cables are suspended at a specific height. Hooks mounted on the booster are designed to latch onto these cables. A buffering system then absorbs the remaining kinetic energy. In simple terms, rather than absorbing impact through landing legs, the system aims to catch the rocket before it makes hard contact. During this flight, an autonomous recovery vessel tested its positioning systems in preparation for such operations. Although the booster splashed down in this demonstration, the infrastructure and coordination elements for future capture attempts were part of the overall test plan. Each of these systems, the heavy lift ascent, the high stress abort, and the sea-based recovery, addresses a different requirement of a future crewed lunar mission. A lunar program is not just about reaching orbit. It requires reliable launch under worst-case conditions, safe crew escape capability, and efficient hardware reuse to manage cost and cadence. On its own, a single test flight does not mean a lunar landing is imminent. But in the context of China's stated goal, placing astronauts on the moon before 2030, this mission fits into a much larger architecture. A crewed lunar mission requires several independent systems to function in sequence. First, a heavy-lift rocket must reliably place large payloads into Earth-Moon transfer trajectory. Second, the crew vehicle must demonstrate safe abort capability under the most stressful ascent conditions. Third, mission planners must develop a repeatable launch cadence, because China's lunar architecture calls for 2 separate launches, one carrying the crew spacecraft and another carrying the lunar lander. If even one of these systems fails, the mission cannot proceed. The recent test directly addressed 2 of those pillars, ascent reliability and crew escape under maximum aerodynamic stress. If the data confirm that the rocket's structural loads, propulsion performance, and guidance systems behaved as expected, this would reduce uncertainty in future flights. If the abort test data validates safe separation and recovery under realistic conditions, it would strengthen confidence in the overall human rating process, the certification that a launch system is safe enough to carry astronauts. The recovery experiment, while not yet a full demonstration of capture at sea, signals an interest in improving operational efficiency. If reusable elements can be safely recovered and refurbished, this could support higher launch frequency in the years leading up to a lunar attempt. There is also a strategic dimension. The United States is developing its own return to the moon pathway under the Artemis program. China, through its independent lunar roadmap and the planned International Lunar Research Station, is building a parallel track. In that context, technical milestones are not isolated engineering events. They are indicators of schedule progress. If China continues validating propulsion, docking, landing, and re-entry systems on time, it would move incrementally closer to a crewed lunar attempt. If delays or technical setbacks occur, timelines could shift accordingly. This test does not settle that question, but it narrows the technical unknowns that must be resolved before astronauts can leave Earth orbit again. Despite the success of this integrated test, several key elements of China's lunar architecture remain in development. The Long March 10 has now completed an ignition flight, but full operational certification will require additional launches. Heavy lift vehicles must demonstrate consistent engine performance, structural integrity across multiple missions, and precise orbital insertion capability. One successful ascent is a milestone, but not yet proof of long-term reliability. The crew spacecraft also faces further testing. While the Max Q abort demonstration validated separation under high aerodynamic stress, future missions will need to confirm life support endurance, deep space navigation, and high-velocity lunar re-entry performance. Returning from the Moon involves speeds significantly higher than from low Earth orbit, and thermal protection systems must withstand that added energy. Then there is the lunar lander. Although ground simulations and gravity offset tests have been conducted, an actual lunar descent introduces variables that cannot be fully replicated on Earth. Terrain irregularities, dust behavior in low gravity, and autonomous hazard detection in real time. In parallel, robotic missions such as Chang'e 7 and Chang'e 8 are expected to gather data from the lunar South Pole and test construction techniques using lunar soil. If these missions confirm accessible resources and operational feasibility, they could directly influence site selection and mission planning for future crewed landings. For now, this recent launch represents one step in a sequence of validations. Each test reduces uncertainty, but none alone completes the system. The next few years will likely bring additional engine firings, docking demonstrations, lander drop tests, and re-entry trials. Each will clarify whether the technical roadmap remains aligned with the 2030 objective. This story is still unfolding. As new tests occur and new data emerge, the overall picture will become clearer, and we'll continue tracking how each milestone reshapes the path to the Moon.